Hello, welcome to Computer Vision Part 2, Session 2 of Course 4 of Technology Fundamentals. In this session, we're going to continue learning how to use convolutional neural networks. In the last session, we talked about three flagship layers for the CNN, three defining layers. Those were the convolutional layers, the rectifying linear unit layers, and the maximum pooling layers. We saw examples of how each of those work. Today we're going to discuss the sliding window. This defines how we pass our kernels over the input arrays, how to build a custom CNN, including higher level architectural modalities, and we'll also discuss data augmentation for images. First, enabling and testing the GPU. So for the first time, we're going to enable the GPU in Colab. We're going to go to Edit, Notebook Settings, and then select GPU as the hardware accelerator from the drop-down menu and hit Save. Then we'll run this cell to make sure we've actually connected to the GPU. Now we'll go ahead and continue on as we're waiting. First thing that I want to point out is the incredible speed up that we get playing with neural nets when switching from a CPU to a GPU. So I have some code here actually borrowed from the folks at Google comparing the CPU to the GPU on some just random neural network that's been created. Doesn't really concern us, except that it does have convolutional layers. And we're going to compare the speed for training these on the CPU or the GPU. And all right, we see a GPU speed up over the CPU of about 80 times. So quite a bit faster to use the GPU rather than the CPU. This should definitely convince us to do so whenever it is available. Importing packages. Today we'll be looking at two methods of importing image data. I think those are really only the new things here today. And just like I was saying, we're going to take a beat here today. When we started building our machine learning frameworks, we simply wanted our data in something like a NumPy array to feed it into our pipeline. At some point, especially when working with images, the data becomes too large to fit into memory. For this reason, we need an alternative way to import our data. With the merger of Keras and TensorFlow, two popular frameworks became available: Image Data Generator and Image Data Set from Directory, which are now both stored under TensorFlow Keras Preprocessing Image. Image Data Set from Directory can sometimes be faster, and that's from TensorFlow. But Image Data Generator, which is from Keras, is a lot simpler to use and has on-the-fly data augmentation capabilities. And I have a link here if you want to see a full comparison between these methods. As we did yesterday, we're going to need to mount our Google Drive. We're going to be reading images in from our Technology Fundamentals data directory, starting with comparing the two import methods. So first, the Keras origin method, Image Data Generator. Pointing to the directory path of where the data is stored, you will need to change the front end of this URL string to point to where you have Technology Fundamentals store. Again, as we talked about yesterday, I suggest navigating to the actual location of the folder, clicking the triple circles and copying the path to replace the front end of this URL. Other parameters we need to set for Image Data Generator: the shape of the image, the batch size to use during training, the training pathway and the testing pathway for the image data sitting in our hard drive space. And we're going to create two different objects.
two different objects, one for training, one for testing. For each one, feeding the relative path. The target size is going to be the image shape. Notice how I've indexed it here, so I'm only including the pixel sizes, not the number of channels. Color mode, setting it to grayscale. The images of these motor impellers that we're using today are already grayscale. Batch size, set to the batch size. Class mode, there's only two classes. These are going to be defective or not defective motor impellers. Shuffle, true, using that for training to just in case there's any weirdness or organization of the training data, we're going to
get rid of that during training so that we don't have artifacts come up when we train the model. For testing, it's not so important because we're not updating the weights of our model according to that data, so not important to shuffle there. All right, run this, and we get our first error message. I think I know where I made some changes today. Tech fundamentals should be in a subdirectory now. There we go. All right, loading the training set, 840 images belonging to two classes. Testing set, 715 images belonging to two classes. Kind of a weird split between train and test. The original data set, and you can visit the URL to access it up here, the original data set had a lot more data in it. For the purposes of teaching this, I didn't want to inundate us with a bunch of data. It takes up limited free hard drive space that we have with Google Cloud. So smaller data set. And the other benefit of this is with this smaller data set, our model's it's going to feel a little bit starved for data. It's actually pretty easy to get a nearly 100% accurate model on this data set with the full data. But with this limited data set, only 840 images for training, we get around 90%. And what's nice about this is we can see how the data augmentation techniques can help us increase this accuracy. So, in any case, if you want access to the full data set, you can visit Kaggle. All right, now showing this with image data set from directory, the TensorFlow version of importing data. Feeding it some of the same stuff here. I got to change this URL as well, fundamentals. I'm just reestablishing these so you see that the same parameters are set in both cases, but what do I want to say? Nothing is changing. Nothing is changing here. All right, some of the hyperparameters, again, very, very similar labels. They're inferred from the name of the file itself for the defective or not defective. Label mode, again, only two classes, grayscale, image size. This had a different parameter name, I think, for the former. They call it target size, but it's the same information. It's just the number of the pixel dimensions. Batch size for training, shuffle true, shuffle false. And that's it. There is an extra step here at the end for the TensorFlow object. You'll notice actually, we've seen this before, even when importing images with TensorFlow, there's a few extra steps. Just take note of this. But also, note that I am overwriting the variables train and test set down here. Moving forward, we're going to use this TensorFlow method of image data set from directory because it runs a bit faster. All right, we can, again, same as yesterday, we can look at some of these images. So here is, what are we looking at? We're looking at the OK motor impeller. We can also look at the not OK. I'm just going to change this to defective. And there's an example of a defective impeller. You see some, what looks like some metal sticking out of the edges. This is not good. All right, change this back because we have a pretty image in the notebook by default. First topic, sliding window. The kernels that we just reviewed yesterday, be them the convolutional sliding kernels or the maximum
the returning maximum kernel, they both need to be swept over the preceding layer, the input layer, and we call this a sliding window, the window being the actual kernel.
And what do we notice about this GIF? One perhaps obvious observation is you can't scoot all the way to the border of the input layer, right? As we're moving this window across the input layer, there's this white border around the output layer that we can't access because we've already hit up against the edge of the input layer when we get to that point. We can change the behavior at the boundary with a padding hyperparameter. All right, so we're going to discuss this. A second observation is that the distance we move the kernel along in each step could be variable. We call this stride. So in this case, the stride is 1. We're moving one step at a time across the input array. We'll explore the effects of each of these, the padding and the stride. And showing where we put those hyperparameters. In this conv2d, I've got strides as a hyperparameter, padding as a hyperparameter, and the same for the max pooling layers. Right? So we have two different kinds of kernels where these hyperparameters are relevant. Starting with stride. Stride defines the step size we take with each kernel as it passes along the input array. The stride needs to be defined in both the horizontal and vertical dimensions. This animation shows a 2x2 stride. So we're seeing here that we're skipping over 1 pixel and going immediately to the next whenever we move this sliding window. The stride will often be 1 for CNNs where we don't want to lose any important information. Maximum pooling layers will often have strides greater than 1 in order to better summarize or accentuate the relevant features and activations. Right? It's
we wouldn't get any data density increase with a max pooling layer if we had the stride set to 1, because we'd return approximately the same number of pixels. So we often have a stride greater than 1 in the case of max pooling. If the stride is the same in both the horizontal and vertical directions, it can be set with a single number, like strides equals 2. So in this case, I've got strides equal 1, strides equal 1 here, and that's fine because we're just assuming it's the same in both horizontal and vertical directions. All right. Padding. Padding attempts to resolve our issue at the border of the input array. Our kernel requires information surrounding the centered pixel. And at the border of the input array, we don't have that information. So what do? We have a couple popular options within the Keras framework. We can set padding equals the string valid and only slide the kernel to the edge of the input array. This has the drawback of feature maps shrinking in size as we pass through the neural network. Another option is to set padding equals the string same. What this will do is pad the input array with zeros, just enough of them to allow the feature map to be the same size as the input array. And this is shown in the GIF below. So in this case, this kernel is a 3x3, and so we only require a padding of size 1 to get us to where we have a feature map that is of the same dimensions as the input array. If, say, for instance, this was a 5x5 kernel and we required information spanning 2 pixel widths around the centered pixel under evaluation, then we'd need to have a padding of 2. So there'd be 2 layers of gray squares around this input array. The downside of setting the padding to same will be that features at the edges of the image will be diluted. All right, an exercise here exploring sliding windows. Just creating some helper functions here for us in order to see this. We're going to create an image and a kernel. Side note, what do we think this kernel is meant to detect for? Notice we've got a gradient that appears in the vertical direction. It's increasing as we go from top to bottom. So what will this do? This will augment, highlight, extract gradients that also are in the input array that appear in the vertical direction and increase from top to bottom. Okay, we will apply our kernel with a 1x1 stride and our max pooling with a 2x2 stride and a pool size of 2. So I've got my convolutional stride set to 1, my pool size set to 2, and my pool stride set to 2. So our convolutional kernel is going to just go pixel to pixel. It's not going to skip any steps. Whereas our pooling layer will take the maximum in a 2x2 window and then take a 2x2 stride. That works pretty well, right? Our input to our filtered, to our detect, to our condensed, we still retain the general structure of the filtered image. We don't lose any information. All right, what about a higher convolutional stride? So pool size, pool stride stays the same, but now the convolutional kernel I'm passing in a 3x3 stride. We see we get a little bit of some funkiness, right? This is no longer a symmetric feature. It's looking a little lopsided. Sometimes published models will use a larger kernel and stride in the initial layer to produce large-scale features early on in the network without losing too much information. For now, without having much experience, it's safe to set conv strides to 1. So we're always going to set this first hyperparameter to 1. Take a moment here with the given kernel and explore different settings for applying both the kernel and the max pool. And I've got a little thought puzzle here for us. Given a total condensation of 8, and I'm taking condensation to mean multiplying the conv stride by the pool stride, what do you think is the best combination of values for conv stride, pool size, and pool stride? And we'll leave this as an exercise. Custom CNNs. As we move through the network, small scale features, those are lines and edges, turn to large scale features, things like shapes, eyes, ears, etc. We call these blocks of convolution, ReLU, and max pool convolutional blocks. Okay, so we're adding some higher order structure here to the language we use to discuss these. So those are called convolutional blocks. And they are the low-level modular framework that we work with when discussing the overall convolutional neural network architecture. By this means, the CNN is able to design its own features, one suited for the classification or regression task at hand. We will design a custom CNN for the casting defect detection data set. In the following, I'm going to double the filter size after the first block. This is a common pattern as the max pooling layers forces us in the opposite direction, right? So as we go deeper into the network, the maximum pooling layer works to constrict the amount of information passing through the network. So a typical thing that you'll see people do when they're building these architectures is increase the number of layers incrementally as we deepen into the network. So I go from 8 kernels to 16, keep it at 16, and then we'll flatten. So remember, yesterday we discussed another option for this is global maximum pooling. Here I'm just going to flatten, and then I'll have my dense head. All right, and I only have one layer for my dense head just to start with. All right, and recall that we are now using the image data set from directory, and this should run for about 4 minutes. We'll go ahead and see if we have anything pulled up. We can just work from some older images or some older graphs as this is running. What I've noticed, and you might notice this as well when you're running this, or you should, the first epoch takes a long time. It's like it's getting booted up, and then as we go through subsequent epochs, you'll see this start to print out faster. Okay, so I've been tracking the loss, so the loss from the training data as well as the validation data set, and then the accuracy. So in blue here is the training set accuracy, and then in orange the validation set accuracy. And we kind of peak at about 90%. I'm not really getting any higher than 90% after about 9 epochs of training. All right, and then we can produce a classification report. Let's see, I believe the one label is labeling defective products. So precision is going to be the ability to not mislabel any non-defective products as defective. Recall, make sure that no defective products are being missed. So we would probably, in a typical setting, this isn't totally ubiquitous, but in a typical manufacturing setting, really want to make sure we don't miss any defective products. So this number here would probably be the most important one to maximize, the recall for the defective products. All right, and then we can create a confusion matrix. One of my
personal favorites. We see on the y-axis is the true labels, the x-axis the predicted. 1 will be defective, 0 will be non-defective. So in the bottom right corner and the top left corner, we'd like all of our numbers to appear here. Looking at the top right, it looks like that we have mislabeled quite a few OK products as defective. It's probably our worst number, but as I was mentioning with this number over here, the recall, the actual ones we really don't want to have are the ones in this bottom left quadrant. Say, for instance, it was really easy to piss off our customers. If we sent them a defective product, we'd really want to move these 7 over to this side. And let's see, no, we're still training. My notes say it took about 4 minutes to do 16 epochs, so we'll see. That was a while ago. It should be the same, and I think it's still kind of stuck on this first round, this first epoch, and it should start spitting out soon. On to data augmentation. All right, so we've done pretty good making our CNN model if that live version reaches the same performance as previously, but let's see if we can make it even better. There's a last trick we'll cover here in regard to image classifiers. We're going to perturb the input images in such a way as to create a pseudo-larger data set. With any machine learning model, the most relevant training data we give the model, the more relevant training data we give the model, the better. The key here is relevant training data. We can easily do this with images so long as we do not change the class of the image, as in change the target label. For example, in the small plot below, we are changing contrast, hue, rotation, and doing other things to the image of a car. And this is okay because it does not change the classification from a car to, say, a truck, if that was indeed the classification task we were trying to perform. Typically, when we do data augmentation for images, we do them online, in other words, during training. Recall that we train in batches, or sometimes called mini batches, with CNNs. An example of a mini batch then might be the small multiple plots shown here. By varying the images in this way, the model always sees slightly new data and becomes a more robust model. Remember that the caveat is that we can't muddle the relevant classification of the image. Sometimes the best way to see if data augmentation will be helpful is to just try it and see. And I'll just walk through this code again while we're waiting for that. Oh, it just finished. Okay, so let's go and take a look at this. It looks like it did 14 epochs. We can look at the loss. So we start really high and then it plummets down. Looks like our training loss was continuing to improve, and val loss maybe after the 5th epoch, maybe the 6th epoch, it doesn't really improve much. Really the 5th, maybe even the 4th. My early stopping was set to, what was my early stopping set to? Patience level 5. So this got dinged right at epoch 9 is when it's said, okay, we're not having improved enough. We can look at the results of this particular round. Not a whole lot has changed there. We shouldn't expect much to change. Our recall for the defective class seems to have gone down. And yeah, again, very similar. This was 7 before, now it's 12. This was still 47. Okay, so not much has changed. We'll go ahead and run this augmented version, see if we get any improvements. Shouldn't have changed anything else. Patience is still 5 based on improvements in the val loss. Oh, notice I don't have the level, the delta set here. I believe by default it should be 1/1000th. All right, so we have a few different things available to us in the Keras Layers experimental pre-processing library for pre-processing or augmenting images. I'm just as an example doing a few random ones. So random flip horizontal will flip left to right, random flip vertical will flip upside down, and then random contrast will change the contrast by up to 50%. And actually, after that very first time loading the data, now even training this new model runs faster, right? That first epoch is what took a whole lot of time. Something weird with, I believe, with the data set from directory method. In any case, it overall runs pretty fast. All right. We'll go ahead and look at the historical for this rather than waiting. So something interesting is our val. So the whole thing runs for longer, many more epochs, right? And this is going to be expected. The training data, it's almost like we have more training data, and so for a given model complexity, to be able to embed the information from that training data will take more epochs. If we increased the model capacity, maybe we would do it in the same number of epochs, but we didn't. Recall for our target class actually went down, so we didn't really get much improvement with those data augmentation techniques. And this is a good note. Well, as we explore this, there's going to be augmentation techniques that are obviously not going to help with this given data, right? In particular, I'm thinking the zoom in feature might be particularly hazardous. Think about it, right? We're already pretty square on the object in question with these images. And if we zoom in too much, we might totally miss what the defect is. So we want to be careful when we're implementing these. And that's going to be our last exercise. These layers apply random augmentation transforms to a batch of images. They are only active during training. You can visit the documentation here. But I've also made this bullet list: random crop, random flip, random translation, random rotation, random zoom, random height, random width. The objective here is to use any combination of random augmentation transforms and retrain your model. Can you get a higher val performance? You may need to increase your epochs, as I mentioned before. And that's it. I guess before we go, we'll go ahead and look at the results from this particular round of training, but I don't expect it to change much. Ooh, big dip there at the end. Classification report. Oh, look at that. Really nice recall on this. Really poor precision, though, for those defective objects. So we're labeling a lot of stuff as defective. Yeah, so we're predicting a lot of good stuff to be defective as well. But if our objective is to not let anything defective go by unnoticed, this would be actually a model we'd prefer. Depends on the cost of mislabeling things as defective. So, all right, that is it. There's another code block down here on transfer learning. I mentioned this yesterday. It's common to take a pre-trained base and attach it to your head. You are welcome to try that here. The particular model I'm using is called Efficient Net B3. I didn't have much luck with this, and again, I believe that our particular task here is a little bit niche and different from what other people have been doing with these types of models. They're typically trying to classify people, cars, objects, things like this, and this is not of that nature. But in any case, the code there is available for you to play with. Thanks.